Hello everyone, welcome to another session of Calculus with Analytics. Today we will talk about limits. Let us first look at some of the limit laws. Sum law. The limit as x approaches c of f of x plus g of x is equal to the limit as x approaches c of f of x plus limit as x approaches c of g of x. Difference law. The limit as x approaches c of f of x minus g of x equals a limit as x approaches c of f of x minus the limit as x approaches c of g of x. Scalar multiple law. A limit as x approaches c of b times f of x is equal to b times the limit as x approaches c of f of x. Product law. The limit as x approaches c of f of x times g of x is equal to the limit as x approaches c of f of x times the limit as x approaches c of g of x. Quotient law. The limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f of x over the limit as x approaches c of g of x, provided the denominator is not equal to 0. Power law. A limit as x approaches c of f of x raised to the n is equal to a limit as x approaches c of f of x all raised to the n. Root law. A limit as x approaches c of the nth root of f of x is equal to the nth root of a limit as x approaches c of f of x. Let us start talking about how to evaluate limits. Think about limits of polynomial and rational functions. If a function is a polynomial function, then the limit as x approaches c of the polynomial function is just equal to plugging in c into that function. That's just p of c. P of x is a polynomial function. And for a rational function, r of x is equal to p of x over q of x. C is a real number, such that q of c is not equal to 0. Then the limit as x approaches c of p of x over q of x is equal to p of c over q of c. That means that for polynomial and rational functions, the first thing that we want to do is to just plug in the constant. Let us evaluate the following limits. The limit as x approaches negative 3 of 4x squared plus 3. What we can do here is just plug in the negative 3 wherever we see x, so that would be equal to 4 times negative 3 squared plus 3, and we evaluate that, we get 39. Once we have a specific number for the limit as we plug in, then that is our answer. We do not need to do anything else. Another example, the limit as x approaches 2 of x cubed minus 17x plus 23. Again, we can just plug in our 2 wherever we see x, so that will be 2 cubed minus 17 times 2 plus 23. The answer is negative 3. And so we are done. Another example, limit as x approaches negative 3 of 4x cubed plus 2x plus 3 is going to be equal to 4 times negative 3 cubed plus 2 times negative 3 plus 3. So we have just plugged in our negative 3 wherever we see x. The answer there is negative 111, and we are done. Now there are some situations where whenever we plug in the value for our input, numerical value for our input, leads to an indeterminate form, and in that case, or in those cases, then we have to do other things. But let us talk about other functions apart from polynomial functions and rational functions. Some of those functions are like trigonometric functions, exponential functions, log functions. These are collectively known as transcendental functions. In that case, to begin with, we can always plug in. Again, we can always plug in our numerical value. And if we end up with a number after we plugged it into the function, then we are done. Okay, so let's try that with a transcendental function. Limit as theta approaches pi over 2 of sine squared pi over 2. That will be plug in pi over 2 wherever we see theta, right? Theta of sine squared theta, that was our original problem. So that will be the limit as theta approaches pi over 2 of sine of pi over 2 squared, and that's going to be equal to 1 squared because the sine of pi over 2 is equal to 1. And so that would be equal to 1, and that's our final answer. Now, the process called factoring and canceling is one of the cases where we would have an indeterminate form, and if we plug in our input, let's say x approaches 1, into x cubed minus 1 over x minus 1, then we get an indeterminate form, a 0 over 0 form. So in that case, then we have to do something more. In this case, we try factoring. So let us see if we can factor an x minus 1 out of x cubed minus 1. And if we know some stuff about the difference of cubes, like x cubed is a cubic, and 1 is also a cubic because 1 cubed is equal to 1, then we could do that factoring. Otherwise, we can just go ahead and set up our long division and do long division and see if x minus 1 is a perfect factor, which we will find out it is, because if we look at the difference of cubes, or if we did factoring, we would have x minus 1 being a factor of x cubed minus 1. So the difference of cubes formula is a cubed minus b cubed is equal to a minus b, all times a squared plus ab plus b squared. So we use that in this situation. So the limit as x approaches 1 of x cubed minus 1 over x minus 1 equals the limit as x approaches 1 of x minus 1 times x squared plus x plus 1 all over x minus 1. Note the x minus 1 in the top will cancel the x minus 1 in the bottom. So we're left with the limit as x approaches 1 of x squared plus x plus 1. Now we can do the step where we plug in our 1. We don't have a problem with the denominator anymore. We don't have an indeterminate form if we plug in, because 1 squared plus 1 will give you a numerical value, and that is 1 plus 1 plus 1 equals 3. Now notice in terms of our notation when we're working with limits, we always drop the limit words at the point or the step where we plug in our numbers, okay? So let's look at another problem where we have an indeterminate form and we have to use another kind of technique. In this case, we're going to use a rationalizing technique to solve our problem. So the question is the limit as x approaches 0 of radical x plus 1 minus 1 over x, okay, over x. So if we use direct substitution, we have radical of 0 plus 1 minus 1 over 0. So that's going to be equal to 0 over 0. So let's use rationalization, or what we call conjugates, to try to solve this problem. So we set up the limit as x approaches 0 of radical x plus 1 minus 1 over x, multiplied by the conjugate over itself, which is radical x plus 1 over radical x plus 1 plus 1, and then do the multiplication, FOIL it out, or if you know something about a difference of squares, you know what is going to be in the numerator is the first number or binomial of the binomial squared and the second term of that binomial squared. So that's going to be radical x plus 1 all squared, which is just x plus 1, and then minus 1 squared, which is 1, all over x times radical x plus 1 plus 1, which is what it was in our denominator. Continue doing this, or expanding, simplifying, and we have the limit as x approaches 0 of x over x times radical x plus 1, and the x's will cancel each other out in the numerator and denominator, so we're left with x approaches 0, limit as x approaches 0 of 1 over radical x plus 1 plus 1. Now we can direct substitute the 0 into the x, so we get 1 over radical 0 plus 1 plus 1, and so that will be equal to 1 over 1 plus 1, which is equal to 1/2, and that is our answer. We are done. Let us look at another situation where we will use a technique called the squeeze theorem. And the squeeze theorem says that suppose x on an open interval, except possibly where x equals c, we have f of x less than or equal to h of x less than or equal to g of x. And suppose the limit as x approaches c of f of x is equal to the limit as x approaches c of g of x is equal to L. So if the highest function and the lowest function have the same limit, then the middle function, which is limit h of x, x approaches c is equal to L. A diagrammatic situation would be just like this. The g of x, which is higher than our h of x, which is higher than our f of x, where they approach a particular x value c, if the limit as x approaches c of g of x is the same as the limit as x approaches c of f of x, then by all means the limit as x approaches c of h of x must be of the middle function, which is h of x, must be the same. Now we can use the squeeze theorem in a situation like limit as theta approaches 0 of sine of theta over theta. In this case, we set up our triangle in our first quadrant. And notice in our first quadrant we have 3 significant lengths here, which is sine theta, theta, and tan of theta. And these we set up as inequalities by using the area of a triangle, the area of a secant, area of the larger triangle. So the area of a small triangle with the height of sine of theta, that area is 1/2 sine theta, which is going to be sine theta over 2. Of the sector, it will be 1/2 theta r squared. That's going to be equal to theta over 2. And for the big triangle, it's 1/2 tan theta. It's going to be tan theta over 2. Now we know that sine theta over 2 is less than or equal to theta over 2, less than or equal to tan theta over 2. We want to use some algebra, do some algebra, because we want to find our half sine of theta over theta in the middle. So the first step, we multiply all the sides by 2 over sine theta, and that will give us 1 less than or equal to theta over sine of theta less than or equal to 1 over cos theta. Then we have to use reciprocals because we want this to be inverted, as to be sine of theta over theta. So if we invert it, notice we have to change the inequality signs, or the inequality signs reverse. So we have 1 greater than or equal to sine of theta over theta is greater than or equal to cos theta. Now it's good to take limits. Limit of a constant is always the same constant. Limit of cosine theta, limit as theta approaches 0 of cosine theta, plug in 0 for theta, the cosine of 0 is equal to 1. So now we have 1 is greater than or equal to the limit as theta approaches 0. The sine of theta over theta is greater than or equal to 1. So by all means, if the limits of the higher and lower functions are equal to 1, thus the limit of the middle function must be equal to 1. So by this squeeze theorem, then, the sine of theta over theta, the theta approaches 0, would be equal to 1 by the squeeze theorem. And this completes as much as we can recall for this section. Thanks for watching. Please like and subscribe, and see you next lesson.